Hey guys, so we have already gone over how to solve a system of equations by graphing. Today we're going to start with our algebraic methods. The first method we're going to use is substitution. This is a great method to use when you have one variable already solved for in one of your equations, like this top equation. The y has already been solved for. So what we are going to do is substitute the y value in the second equation for what it was equal to in the first equation. So what I'm going to do is I'm going to put parentheses around what y is equal to, the 6x minus 11, and I'm going to place it inside the second equation in place of the y. So it'll look like this. If I rewrite the second equation, negative 2x minus 3, I'm going to replace the y with 6x minus 11, and then finish my equation. And there you go. So I have combined both equations into one long equation, and all I did is I took what one variable was equal to, what the y was equal to, and I replaced the y. So now I have a single equation with only one variable, just x. So I can solve this. So my first step is going to be to distribute this negative 3. Be sure you distribute a negative 3, not just the 3. So negative 3 times 6 is negative 18x. And then negative 3 times negative 11 is positive 33. Now I can combine like terms. Those would make negative 20x. We'll minus 33 to the other side, trying to get the variable by itself. Negative 40, and our last step is to divide. So we get x equals 2. Now I'm not done with this problem because we still need to figure out what the y value is. So I'm going to go back up to that first equation. We could use either equation, but I'm going to use the top equation because it's going to be easier since y is already isolated. I'm going to replace the x with its value, which is 2. So let's solve this. I'll start by distributing. We get y equals 12 minus 11. So then we subtract that and we get y equals 1. So I'm going to write my answer as an ordered pair. X comes first and then y. So the solution to this system of equations is 2, 1. If we were to graph it, that would be the intersection of these two lines. Okay, let's try the same thing on this problem. Again, on our top equation, the y is already solved for. It's 5x minus 7. So I'm going to replace that in our second equation. Okay, so now I can distribute the negative 2. My next step is to combine like terms right here. Let's start getting x by itself. I'll need to minus the 14 to the other side. Almost done, we just need to divide. Alright, so we get x equals 2. So now that I know my x value, I can come back up here to the top equation and I can replace my x with 2. Okay, let's distribute. We get y equals 10 minus 7. Subtract that, y equals 3. Let's write our answer as an ordered pair. So that's going to be 2, 3. Now in this example, we don't have a variable that's already been isolated. So we're going to have to do that part ourselves. I'm going to look at both equations and figure out which one would be easier to work with. For this one, I think the bottom equation is going to be easier because I see the y right here has no coefficient, which is the number in front. There's always an imaginary 1, but I like it when there's no coefficient in the front because that's going to take me less steps to get the variable by itself. So working on my second equation, if I want to get y by itself, I just need to add the x to the other side. So I get y equals And on the right hand side I have 3 plus x. And I'm going to write it just like that, 3 plus x. I cannot actually add those two together, so I just leave it. Now it looks more like our first two examples. I have y already by itself is equal to 3 plus x. So I put that in parentheses, and I go and plug it into the opposite equation. And so this is what I get when I replace the y with 3 plus x. So let's start solving. Let's distribute. We get negative 3x plus 9 plus 3x equals 4. We need to combine like terms, so negative 3x and a positive 3x, put those together. That would equal 0x. I don't need to write 0x, it means I don't have any x's. So let me just write what's left. 9 equals 4. This is very different. I don't have any more variables. So I cannot continue to solve for x because I don't have any more x's. So when that happens, that doesn't mean that you did anything wrong. You need to stop doing the problem, look at your statement that you have left, which is 9 equals 4, and determine if that is true or false. This is false. 9 does not equal 4. And so that means that we have no solution. So these two lines do not intersect. These two lines must be parallel. So here's our last example. I'm looking at both of my equations, and neither one of them have a variable already isolated. And they all have a coefficient because technically this y on the first equation has a -1 coefficient, so that would still require me to divide in order to get it by itself. So I'm going to go with this bottom one because look, the y is almost by itself already. I just have that 3 that I need to get rid of. So to get y by itself, I'm going to divide everything by 3. So I get y equals 2x minus 3. Now y has been isolated. I'm going to take what it's equal to, which is 2x minus 3, and I'm going to go up to the top equation and replace the y with 2x minus 3. This is what I get when I replace the y with 2x minus 3. I don't have a coefficient because there was no coefficient in front of the y, only the negative sign. But this looks a little weird. I almost feel like I need to distribute that 2x, and that's not the case. I need to distribute this negative sign. So I'm going to put a 1 right here so I can actually multiply something besides just a sign. So that'll be 2x. Negative 1 times 2 is negative 2x. Negative 1 times negative 3 is positive 3. And now I can combine like terms. 2x minus 2x. Hey, those cancel again. So let me write what I'm left with, which is 3 equals 3. So my variables have canceled out, so I stop doing the problem. I look at what I have left and determine if it's true or false. Does 3 equal 3? Absolutely, that's a true statement. That means I have infinitely many solutions. So on a grid, these two equations would actually be the same line. They just look a little bit different because of how they're written. So we can still have no solution, infinitely many solutions, or one solutions when we're solving a system of equations algebraically. If your variables cancel out, look at the statement that's left. If it's true, there's infinitely many solutions. If it's false, there's no solution. Alright, now it's your turn. Try this system of equations and we will discuss it tomorrow.